Greetings, dear colleagues. My name is Daniil, and I'm from Kharkiv National University of Radio Electronics in Ukraine. And today I'd like to introduce you to our research on how we can use machine learning techniques to recognize human emotions through speech. Human emotional states can be detected and analyzed in various ways, and one promising method is speech analysis. Such tasks can be simplified and, of course, automated. Our main goal in this research was to identify the most effective artificial intelligence method among the currently most popular ones for the speech emotion recognition task. We also had the task to analyze the available datasets in this domain, considering techniques for data extending through augmentation. Finally, we need to build models and compare them using evaluation metrics. Understanding emotions from speech can significantly improve smart home systems, medical applications, and even emergency services by providing more empathetic and accurate responses. We also reviewed the previous works. They often used deep learning to solve their SER task. We reviewed several papers that use different data and managed to achieve a model accuracy of more than 90% and even 95%. And the most popular approaches for this task were recurrent networks like LSTM and GRU, and of course convolutional networks. Recurrent neural networks are designed to deal with sequences of data where information is passed through time. The basic idea is that there are links in the network that create loops, allowing information from previous time steps to influence the current state of the network. However, regular recurrent networks have vanishing and exploding gradient problems. So, recurrent networks based on GRU and LSTM units were created to improve the network's ability to store long short-term relations. Such units, like LSTM and GRU, use so-called gateways to select which information to remember and which not. GRU has a simpler structure than LSTM, which should theoretically speed up the training of the network based on it. A convolutional network is a deep neural network specifically designed to process and analyze structured data matrices. There are several main components in such a network. First, convolution layers, which use trained filters to perform a convolution and pattern extraction. Second, pooling layers for matrix reduction and highlighting of the most significant features. And third, fully connected layers for classification itself. So we decided to use in our study the following models, the following methods. CNN as one of the most successful methods among the ones reviewed, BLSTM and GRU, which are improved recurrent networks methods, and combination of CNN and LSTM to show the potential of the hybrid approach for this task. There are many public datasets that have been developed for the task of speech emotion recognition. We compared datasets such as SAVI, RevDes, TAS, GrammarD, and AMACAP. The slide shows a comparative table of these datasets. Among them, we were able to identify quite impressive sets in terms of the number of samples and their variations. Finally, we have chosen the following. GrammarD. It contains audio and video recordings of 91 actors expressing 6 different emotions: happiness, sadness, anger, fear, disgust, and neutral, for a total of 7,442 samples. And AMACAP, which contains interactive sessions between actors, in other words, live communication, with 10 emotions with more than 12 hours of audio data. For our experiments, we focused on 4 specific emotions: anger, happiness, sadness, and neutral state, in order to maintain a balanced and manageable dataset for model training and evaluation. To improve the robustness of our models, we applied several data augmentation techniques. These are the most common techniques in audio processing, and they include noise addition, time stretching, and pitch shifting. Data augmentation proved to be a key factor in improving the performance of the models, highlighting the importance of using augmentation for the SUR task. Since neural networks often operate on numerical values, we need to convert our data into numbers. We distinguish three types of audio features. Time domain features. They provide information about signal amplitude and changes over time. Frequency domain features describe the distribution of energy among different frequencies in the signal. And time frequency domain features, they are the most informative because they show how frequencies change over time. MFCCs are time frequency domain features, and they are widely used because of their effectiveness in representing sound features relevant to human speech perception. The current slide shows a representation of MFCCs. Each bar is a frame of our audio signal. Each row is a particular coefficient. There are 13 coefficients here, but there can be as many as you like. However, it's important to remember that the most informative are the first ones, as you can see in the picture. Since we decided to use MFCCs as audio features, the algorithm for extracting is the following. Divide each audio into frames that partially overlap each other. The overlapping is necessary to preserve the connections between the frames. Also, we used a dynamic frame size approach, so that each audio signal is fully utilized regardless of its duration. Apply windowing function so that there is no spectral leakage when transforming from the time domain to the time frequency domain. Transform the frames into a time frequency sequence, obtaining a spectrogram, and extract coefficients from the MEL spectrogram. To evaluate the models, we use several common metrics such as accuracy, precision, recall, and F1 score. The model testing process itself was done using k-fold cross-validation as one of the most objective. In the process of creating the models, we of course use the Python language. The basis of working with audio, especially for feature extraction, was the Librosa library. The development was done in Jupyter Lab and Keras was used for model building. Here are the four models that have been developed. The recurrent models contain two layers, each of BLSTM and GRU, with additional dropout layers to prevent overtraining. The convolutional model contains 6 blocks. Each consists of a convolutional layer, normalization, pooling, and dropout. The hybrid model has 2 LSTM layers after the 6 convolutional blocks. The rest of the details can be seen on this slide. The training plots of the models you can see here, both the convolutional and the recurrent ones are similar to each other. You can clearly see that the recurrent ones are faster to train. However, all models are poorly and overtrained. This slide shows plots with the augmented datasets. You can see that the training was more stable, and in the case of convolutional networks, overtraining is not even noticeable. If we look at the F1 score for the 2 datasets without augmentation, we can clearly see the impact of class unevenness. For example, for the CNN model on the IMACAP dataset, the F1 score for happiness is only 0.26, while for the other classes, this value exceeds 0.6. On the other hand, there is no such problem with the CREMA-D dataset. If we look at the same model but on the augmented datasets, we can see that the difference in the F1 score value between the classes has significantly decreased, and for all of them exceeds 0.97. Here we can see the accuracies of the models with and without augmentation. We can clearly see a significant increase in accuracy with extended datasets. We can also see that the convolutional model is the leader under all conditions. To sum up, among the models developed, the convolutional layer model showed the highest performance. It was also found that the dataset with the more evenly distributed classes achieved better accuracy. Regarding the augmentation, we found that it's very important. It gives an accuracy boost and allows to compensate the non-uniformity of classes. Also, the obtained accuracy results show the highest performance among the reviewed works. As further research, we can propose the use of visual data to solve the SER task. We can also explore other types of models, different combinations of datasets, as well as more in-depth research of audio features with subsequent implementation of a software system based on the obtained models. Thank you for your attention.